When you look down at the Earth from space, you notice that massive storm systems don't sit still, they spin. If you track a hurricane forming in the Northern Hemisphere, like this one off North America, the clouds always rotate counterclockwise. But if you look at a cyclone forming south of the equator, off the coast of Australia, the rotation is entirely reversed. It spins clockwise. The invisible force driving these opposing rotations is called the Coriolis Effect. It sounds like a complex physics concept, but we can prove it exists right now by building a physical model to map it with your own hands. You only need a few items: a turntable or lazy Susan, a large sheet of paper, some tape, and 3 markers. Understanding this effect bridges the gap between simple planetary rotation and the massive weather systems that shape our world. To start, place your paper over the turntable and center it as best you can. Tape down the edges securely. You want the paper completely flush so it doesn't catch or slide around when the table starts moving. Before we simulate a rotating planet, we need to establish a control test, a baseline to show how objects move on a world that sits completely still. Make sure the turntable is entirely stationary. Take your first marker, place it near the far edge, and draw a line directly towards your body. Look at the result. The line on the paper is perfectly straight. This step proves your hand is pulling the marker in a straight, unbending path, which isolates the variables for our next tests. Without planetary rotation, moving objects like wind or ocean currents would behave exactly like your marker, traveling in straight, uninterrupted paths across the surface. Now let's simulate the Northern Hemisphere. To do this accurately, imagine you are looking down at the Earth from directly above the North Pole. From that northern perspective, the Earth rotates counterclockwise. So you'll need to spin your turntable counterclockwise to match. Make sure you clearly establish this counterclockwise direction before moving on to the next step. Practice spinning the table a few times. You or your partner need to maintain a perfectly smooth, constant speed. Once you have a steady spin going, take your second marker. Start at the edge and pull a straight line directly toward your body, exactly as you did in the baseline test. Focus on moving your arms straight back. Resist any urge to curve your hand and let the spinning paper do all the work. When you stop the table, the result is completely different. The line you drew is a severe curve to the right. This rightward curve is the Coriolis effect in action in the Northern Hemisphere. As air flows across the rotating surface, it deflects to the right, creating the counterclockwise rotation we see in hurricanes. Let's shift our experiment to the Southern Hemisphere by changing our perspective to a vantage point below the South Pole. From underneath, the Earth's rotation appears reversed. Instruct your partner to spin the turntable in a clockwise direction. Keep that clockwise spin steady and consistent. Take your third marker, start at the far edge again, and pull a straight line toward your body while the table rotates. This time, the line curves sharply to the left. Compare that directly with your previous test. The rightward curve from the north has completely flipped. Simply changing the hemisphere, and therefore the relative direction of the planet's rotation, reverses the apparent deflection of moving objects. That is why southern storms are forced to spin clockwise. Stop the turntable completely and take a look at your completed map. You have 3 distinct paths: a straight line representing no rotation, a rightward curve for the north, and a leftward curve for the south. This introduces the core concept in physics, a frame of reference. You know your hand moved in a straight line, but from the reference frame of the spinning turntable, the path was deflected. Because humans live on the spinning surface of the Earth, we share its frame of reference. We perceive that same curve in the winds around us, and this rule of physics applies to any rotating planet in the solar system, including Mars. Take a look at these bright, curved dust streaks trailing from the craters in the Hesperia Planum region. By analyzing the curve of those streaks, we can deduce the wind direction and confirm that the Coriolis effect is actively shaping Martian weather. The Coriolis effect is a universal consequence of rotation. Your simple turntable model accurately maps the exact same atmospheric forces governing planets across the solar system.